I like to deal with this example today. I will do one so there's 3 or 4 examples I'd like to get through. But we're going to do one of them today and then move into trigonometric equations. We'll come back tomorrow, maybe do this second example here in 7, and then work with trigonometric equations. Just to give a little bit of a break between these types of problems that can be, I think, somewhat frustrating for students sometimes. Okay. The issue with these are understanding that this input that they provide me, because X is our input, right? It's arbitrary. Okay. I do not know what it is. Okay. But when they write cosine inverse of X, that green thing right there, they are implicitly providing me some angle. Okay? Now, because X is unknown, X is variable, it's general, okay? Then that means the angle that is going to be the output of that thing is also general or unknown. Does that make sense? Okay? I think it makes sense maybe to be able to grasp that idea by doing a problem where X is not general. Okay? So let's say I give you sine of 1/2 cosine inverse of, let's just say, 2/5. Okay? If I ask you that is now a specific ratio, correct? So because I know that specific ratio, we should be able to take our calculator and ask our calculator for the specific angle that goes with that, 66.4 degrees. Okay? Now, the one thing to know is that angle, because it's cosine inverse, that output can only be between 0 and 180, and 66.4 is. So basically what they're saying here, when I know that specific value, I know the specific angle to be sine 1/2 now, that specific angle is 66.4 degrees. Which can I rewrite that as sine 66.4 over 2? Now, I could grab my calculator and let my calculator evaluate that, but I could also tell my calculator that that's going to be the same thing as 1 minus cosine of 66.4 all over 2. That's the half angle formula for the sine. So 66.4 over 2, maybe you would see it written that way instead. And you can see now that the comparison, if that's 33.2, then over here, the argument in the cosine is twice that. But I can only do that because I know the specific 2/5. So when we have an arbitrary value for my ratio, okay, that ratio is adjacent divided by hypotenuse, right? So when they give it to me as arbitrary, they're giving me then an arbitrary angle. And I say arbitrary, which basically means they're giving me X to be anything. Now, I need to know that there are constraints on the cosine inverse function. So they're telling me X is any number between -1 and 1, right? So they're implicitly telling me then that the angle that I'm interested in is any angle between 0 and pi, or 0 and 180. Does that make sense? Okay. So I've got an infinite number of possibilities that could come out here because of the generalities here expressed with that variable. So because of that, the only way that we're going to be able to gain what we need is to draw a picture. If they tell me cosine inverse of X, that's going to produce some angle. I don't know what that angle is because there's so many different angles it could be. Okay? But because X is positive, okay, so that ratio of X can be rewritten this way, right? Because X is positive, and that's the adjacent side, and my hypotenuse is positive, that tells me that the cosine inverse of X is producing an angle that's in the first quadrant. Okay? If X was negative, it would tell me that I'm working in the second quadrant. Okay? And I know I can't be working in the third quadrant, even if X was negative, or the fourth quadrant when X is positive, because the cosine inverse is only defined for the first and second quadrants. Okay, so that's the only half plane that you can operate in with the cosine inverse. So we know that this is x then, and we know that that is the hypotenuse. Therefore, with that general or arbitrary value for the adjacent divided by the hypotenuse, that is going to generate that arbitrary angle theta. So this thing here provides that theta. Is that okay with everybody? So I can rewrite this now as sine of 1/2 theta. Now we don't end up needing this, but I think it makes sense to maybe find this vertical distance because tomorrow when we do this problem, we will need it. How do I find that vertical distance right there? Yes, so I'm going to use Pythagorean Theorem, right? And I'll get square root of 1 minus x squared. Good. Is everybody on page with that? Okay. So now, some textbooks will define the sine half angle formula this way. Our textbook defines it this way. They're the same, right? Okay. Now, the theta that we have is this theta. Okay. Now, we know that it is occurring between 90 degrees and 0 degrees, right? So my result when I'm done should happen between 0 and 45 degrees. Does that make sense? Because this is theta, so half of theta needs to, you would do that with those values. So now we would reside between 0 and 45 as the final answer, or 0 and pi over 4. And when we're done, we'll see, we'll try to graph this and demonstrate that that range. Yes? We know it's in the first quadrant because the cosine inverse is only defined because the cosine inverse, you can only put numbers in between -1 and 1. That's the domain for cosine inverse. And when I plug those in, I plug -1 up to 1 in, the only thing that comes back is 0 to pi or 0 to 180. So because the cosine inverse is the nested function here, we know it can only work in the first or second quadrant. Because the x is positive then, that eliminates being able to use the second quadrant because there the x would be negative. Does that make sense? So that's why we're only in the first quadrant. If they gave me a negative x here in the ratio, then they'd put me over here in the second quadrant. So now the sine function, because I know I'm in the first quadrant, and the y value, if anything in the first quadrant, is positive, right? So if we go back to our sine half angle formula, it's a positive or negative formula because of the radical. But we know we're in the first quadrant, and y values are only positive in the first quadrant, so we're going to go with that one. The sine function for the half angle is 1 minus cosine of theta divided by 2. So now what is the cosine of theta? Cosine of theta is x over 1 here, right? So this thing here changes to x, so I get 1 minus x over 2. And that then is the exact same thing as that there. But this was trigonometric, right? Sometimes referred to as maybe transcendental. This is purely algebraic. Okay? Non-transcendental. Okay? So what does that mean to... So I talked in the last... And I don't know. I'm hypothesizing this, but... I do know a little bit about like programming and like using you guys know what Grove is up by Finley, or not Finley, Bluffton, across from the water tower in Bluffton on I-75. It's a German robotics company. Okay, they manufacture their headquarters. Like I think their headquarters for North America are Bluffton, Ohio. Okay, but they make CNC machines, which are like computer run You guys know what a router is, okay, or a milling machine. Basically what it does, and in their machines, I think they use 4 axes, which is, and it basically allows you to work in 3-dimensional space, but there's also the ability to rotate the piece that they're working on. So I think their website has some pictures on it, I think. So these are some of the CNC machines that they make, which, if you look in here, kind of zoom in, maybe on the picture, that's not a very good picture. So you can find some more. All right, so this is kind of a, I don't know if this is a video play. Let's see. All right, so the movement of these axes that allow this shape to move, and we can kind of move through. So they're making Eiffel Tower here, but eventually they'll probably start. So they start rotating this in 3 dimensions, so that this cutter can stay. You kind of see that movement there. That programming that gets done with those movements, okay, and that robotic, and you also see, you guys have seen like robotic arms on like assembly lines, these types of things, okay. They move in 3-dimensional space, and some of that programming, they use matrices and vectors to do that, but the programming maybe in moving in 3-dimensional space could maybe be done with this. But if I do that then, and I program and code things with that function, now my program has to have built into it an understanding of what the cosine inverse is. So if I put some x value in there, it's going to have to reference the cosine inverse function, figure out, okay, if I take x and evaluate on that, and now evaluate, get that output, and put that output here, and then evaluate sine half of that output. Does that make sense? So I've got to have in my program, in the background, extra functions that my input is going to reference to, okay? Well, if I take that function right there, that is purely trigonometric, and run through the algebra, the geometry, the trig, and I get square root of 1 minus x over 2, now my program doesn't have to reference any trigonometry. Does that make sense? So it makes that program cleaner, runs faster, saves RAM, saves money, which is a good thing, okay? But a lot of the stuff that we do with robotics and how it's, and that's very simplistic explanation. You get into vectors and eigenvectors and eigenvalues and stuff like linear. It's called linear algebra. Basically using matrices to solve movements for us, and it has a kind of underpinning or foundation in trigonometry and this type of stuff. Okay, so it's because people always ask, where in the world am I going to use this? Okay, I'd say 99% of us probably aren't ever going to use this again. Okay, but some of them might go into engineering or something like that eventually. Maybe you come across this again. Okay, but to show like a real world application, I mean, there's so much more other information that we have to learn and know to actually apply that. Does that make sense? And that's kind of what I dislike about math, especially when we get higher level math and we're just doing like these practice problems. People always ask, where can I use this? I can show you, but there's from where we are now to where you would actually then use it, there's such a big gap of information there that we have to learn to actually then apply what we're learning now. We'll come back to a couple more of those. Actually, no, I'm sorry. Let's actually graph that first. before we go on to trig equations. So we were talking about 1/2 cosine inverse x being that inner function, then we'll take the sine of that. So if I were to type that into Desmos, now just think about this real quick. Would you agree, or what is the, because it's a nested function, I'm only going to get an angle back out of the cosine inverse of x if I use x values that are appropriate. If I use an x value of like 5, so let's go arc cosine of 5, I get undefined back, right? Okay. But if I use 0.5, I get 60 back. I get a defined value. What are those values that I'm allowed to use here for the arc cosine? -1 to 1, okay? So the arc cosine from -1 to 1, and I'll put this in radians so it's easier to see. My arc cosine is only defined for those values between -1 and 1, okay? So when I take the sine of 1/2 of that, okay, you can see why only the values between -1 and 1 are being graphed there. Does that make sense? Okay, and it's because I can only do algebra, I can only do and trigonometry with defined values. Okay, so outside -1, +1, I cannot then get y values back out of this function if the inputs were undefined. So that's why that thing is cut off there. Okay, now if I type in a completely new function, square root of 1 minus x over 2, now we see that there is some overlap here. There is some overlap, okay? But the red function keeps going on forever, right? But what we need to be able to do is realize that this red function is supposed to be a replacement for this function. And if this function was only allowed to have x values between -1 and 1, then this one is only allowed to have x values between -1 and 1. And when we restrict that, then we do get the exact same stuff, right? That makes sense to everybody? Okay. What is the... we won't talk about it. Let's go down here to this. So solving trigonometric equations. So we'll come back and do some more of those examples tomorrow that ask a similar procedure like we just did. But I'd like to get into trigonometric equations with you a little bit, just touch basis on really the last two steps of every trigonometric equation we're ever going to come across. Okay. Trigonometric equation is just an equation in which there is a trigonometric function involved. Okay. Now, it does not mean that every function or every equation that has a trig word in it is going to be considered a trigonometric equation. So, for instance, if I say x plus 1 equals 2 tangent of 45, that is not a trigonometric equation, okay? Because what's tangent of 45? It's 1. So I really got x plus 1 equals 2 times 1, or 2, and that's a linear equation, isn't it? Okay? But if I wrote something like this, that is now a trigonometric equation. And the reason we classify it as a trigonometric equation is because the argument here is variable. Okay? Here, the argument was not variable. Does that make sense to everybody? Okay? I don't think you'll ever see in this class anything like this. I mean, they're all going to start. I'm not going to ask you to classify whether something's a trigonometric equation or not. but that's the comparison between an algebraic and a trigonometric. My main goal for us is to obviously solve these, but I like this last goal here. It says accurately classify trigonometric equations into categories in an effort to draw comparisons between previous and current equations. That in itself is everything we've been doing since we started Algebra 1. Okay? Every single type of equation you come across, you categorize it. Okay? So, for instance, if I had ax squared plus bx plus c equals 0, we categorize that. We say, okay, what if a is 1? Does that give us a separate technique to solve that equation if a was 1? And then we had a situation, well, what if a is not 1? Doesn't that lead us to the AC method? Okay, or factor in GCF out. But regardless, if a is not 1, it's a different approach than what it was when a was 1. If we have those two things, great. One of those works, that's awesome. If one of those doesn't work, then don't we have the ability to use this thing? Right? And we spend a lot of time in Algebra 2 and college algebra analyzing ax squared plus bx plus c equals 0, that type of equation, and developing basically these three categories of approaches to be able to solve those. Okay? And then we built on that and say, okay, well, what if it's not a quadratic? What if it's just polynomial? And then we can categorize polynomial equations based on maybe whether they all have a common factor, a GCF in them, and then maybe if they're trinomial, we use one approach. If they're quartic, we use another approach, but collectively we can use P over Q or rational root theorem. But we categorize types of functions, right? And that ultimately categorizes the equation and then sends us on a pathway to be able to solve it. Same thing happens with trigonometric equations. The hope is that we can start to categorize the type of problem that we see and realize, hey, that problem I'm working on now looks like question 1 that we did in class. What did I do in question? Even though it may be different trig functions, but the structure is the same as question 1 that we, or example 1 we did in class. Use what I learned from example 1 in class to help with what I'm working on now. Does that make sense? So my hope is that we realize that not every one of these problems we ever come across is completely unique and different than previous ones. Okay, use previous knowledge, what we've learned, previous experiences to help us navigate the current problem. So these are examples of trigonometric equations. Okay, we've already talked about that first one, it's an identity. But those second and third equations up there, 2 sine theta minus 1 equals 0 and tangent 2 theta minus 1 equals 0. The variable part is the theta, okay? And they'll jump back and forth. They'll use theta, they'll use alpha, they'll use x, they'll use t. Doesn't matter what the variable being used is. We are looking to find an angle measurement, okay, when we deal with trigonometric equations. What I want to do right now is just draw a comparison to what you did in Algebra 1, or maybe even pre-algebra, 7th and 8th grade math, okay? If I gave you this, is that an equation? Yeah, some people think it's kind of a trick question, but it has an equal sign, right? It is stating that two things are equal, so that is indeed an equation. Is it a trivial equation? Meaning, is it kind of boring to work with? Yeah, it's already solved for, right? Okay. So if I started you with that and I asked you, well, solve for x? It's already done. Okay. That's kind of what we're seeing right here in this problem. Okay. We're kind of almost done. Okay. This is a trigonometric equation. It's trivial. It's kind of boring. Okay. I could make this algebraic equation a little bit less boring by maybe starting you with the previous step that I would have gotten if I worked backwards, right? Does that make sense? So 2x equals 1 is probably where x equals 1/2 came from. Much like this one, okay, if I work backwards on this one, maybe 2 sine of theta equals 1 is where this sine of theta equals 1/2 came from. Does that make sense? Okay, and maybe even before that, maybe It came from 2 sine theta minus 1 equals 0, which is that equation right there. Does that make sense? So what I'm showing you is algebraically the last step of every trigonometric equation you'll come across. Okay? Now what we have to do is, once we get to that last step, is actually figure out what theta has to be. Okay? So we're trying to, the way I teach this is kind of reverse. I'm going to show you the trigonometric approach at the end of every problem. We're going to learn that and get good at that, and then start working through more complex trigonometric equations that involve algebra that we will dwindle down to this, and once we get to this, then we utilize the technique I'm going to show you right now, okay? Which is a technique we've already talked about, but now you see the application of it. So this says solve the equation sine theta equals 1/2 within one period. So within one period, what that means, what is the one period of the sine function? 0 to pi. Okay? And a lot of times they write it that way. They'll enclose 0, they'll include it, and then they'll leave 2 pi open. And the reason they do that is because it's the same point on the unit circle, isn't it? So they'll leave one open, one closed. It doesn't really matter. But that's saying one period. Sometimes they'll say find all solutions. We'll talk about this at the end, but that's an infinite number of solutions then. So we'll have to write some equations to show our answers. Sometimes they'll say find the answers between 0 and 4 pi, or 0 and 5 pi, or negative 2 pi and positive 2 pi. So we're always got to pay attention to kind of the window they want us to find our answers in. Okay, and this one, the window is between 0 and 2 pi. All right, so this is how we're going to do this. You're going to get down to the point where you get sine of theta is equal to 1/2. So now what we're trying to do is we're trying to figure out what is the theta, okay, what angle measurement do I plug in to spit back 1/2 as a y value? Does that make sense to everybody? Okay. Now, you might know that already, but I want to show you the algebraic approach to this, because this could eventually be like 2/3. And that's not from the unit circle, right? So I want to show an approach that you would use regardless of whether the value is on the unit circle or not, or I guess a known value on the unit circle or not. So how do I get this theta out of those parentheses, out of that argument? Sine inverse, okay? Much like when I would have solved like radical x equals 2, the only way I can get that x out is to use the inverse of the root, right? So I'm going to use the inverse of the sine function here. So when we do that, and this is why those previous questions that we were doing at the beginning of the period and that we did previously through chapter 6, why this is important, okay? We know that the sine inverse and the sine, they will cancel and give me theta, but they will only cancel and give me theta on the interval or the range of negative 90 to positive 90. Does that make sense? Okay. That is the only way that we can get a direct cancellation for the sine inverse and the sine. Okay. Now, what I want you to understand is that when I say sine of theta, that theta can be anything. Okay. Let's look at this real quick. If I graph sine of x, that's that graph right there, right? And the input x is all these values on the x-axis, okay? So basically what we're saying is that I could take a value, okay, and I'll just go from that number there to that number there. But when I play this, there will never be, I'm going from negative 11 or negative 111,101. That's a hard number to say. So I'm 100,000, negative 100,000, positive 100,000, and I never get a situation where it does not evaluate and give me an undefined value, right? Okay. So x can be anything. Okay. X can be anything there. Okay? My input can be anything that I want it to be. The sine inverse, though, that input is not allowed to be anything, right? It can only be -1 to 1. Okay? So when I look at those two things right there, the only way that they're going to cancel is if they are overlapping one another, right? They're sharing the same x values. Okay? So the only way they're going to cancel is if I use values between -1 and 1. And the only values, okay, if I use, a slider here between -1 and 1, these values that I get back here, put this in degrees so you can see a little bit better. Oh, I'm sorry. I want the arc sign here. The only thing I'm getting back are angles between -90 and +90, right? That makes sense, everybody? So, why do we talk about that? We want direct cancellation so we can address the theta. Okay? So then when I come over here and I use that relationship to get that theta to fall out, we use the relationship that the sine inverse is only going to spit back an answer between -90 and 90. Meaning that when I use sine inverse over here, I'm only going to get an answer between -90 and 90. Does that make sense? We can evaluate that. Now that is it's all variable, it's all specific values on the right hand side. Sine inverse of 1/2. There's no variables over there on the right hand side. So you can evaluate that. I can either grab my unit circle, I can go from memory, or I can use my calculator. And if I say sine inverse of 1/2, what am I going to get back? If I think about my unit circle, I think about the y values that are between -90 and +90, because those are the only ones I'm allowed to use here because of the cancellation concept that we employed. The only angle that comes back that has a y value of 1/2 is what? 30. Okay? Okay, so the y value is 30. Okay, 30 degrees, or if I'm in radians, pi/6. Okay? Now, that gets us that answer. Okay? But initially, the problem, sine theta equals 1/2, did not know that we were going to employ an inverse function that was restricted to -90 to 90. Okay? Because think about what we're really doing here. If I think about a graphical approach, okay? Well, let's look at a unit circle approach first. If I look at a unit circle approach, what we just said was, looking at the unit circle, the sine function, the y value, having a coordinate of 1/2 happens right there, correct? Is there anywhere else that the y value ends up being 1/2 on the unit circle going in one period from 0 to 2 pi? Is there anywhere else that I get a y value of 1/2? Quadrant 2 right there, correct? And if this was 30 degrees right there, how big is that angle? 30 degrees. So what is then, from standard position, that angle there? 150, okay? So theta could also be 150 degrees. We don't get that from our calculator because our calculator, we use the sine inverse. Sine inverse is only going to give you something between -90 and 90. It will never give you that 150 back. Does that make sense? So we have to use that understanding to get to 150. If I think about it as a function instead of the unit circle, let's go look at the sine of x. And I will put it in radians here and make it a little bit easier. Okay. So when I look at the equation sine of x equals 1/2, that is asking then, when does sine of x's curve cross the 1/2 curve? And it's the x, just like any other equation we've ever seen since algebra started, it's the x value of where they cross, right? Now we're saying at the onset of the problem that we only wanted to look on one period. So I'll do that. and that as well. Okay? So only looking on one period, so I shorten the functions down, right? Is that x value the one that we found? But we see this other one that our calculator will not generate, and it's 5 pi over 6, which is what in degrees? 150. Okay? This second one will never be produced by your calculator because it's outside of that negative 90 to 90, or that negative pi over 2 to pi over 2. So we have to do a little bit of thinking outside the box to get it. Okay? All right. So if they wanted me to do this on an infinite scale, okay, so right now, on the interval from 0 to 2 pi, we found the answers of theta to be pi over 6 and 5 pi over 6. Okay? If we look on the scale of 0 to 360, we're looking at theta being 30 degrees and theta to be 150, right? Okay, those things say the same thing, just in different units. So that's radians, and that would have been degrees. If they want all possible solutions, there's an infinite amount of them, right? The first one is going to happen at pi over 6 or at 30 degrees, right? Now let's look back at our graph then. Okay, let's make this thing go to 4 pi real quick. And now you get, so we had these two solutions previously. Let's look at this one. Because that one right there, because of the period relationship that occurs with the sine curve, is that one right there corresponding to that one right there. Okay? What is the difference in those two coordinates? 2 pi. 12 pi over 6, right, on the x coordinates? Or the x values. So, how do if I know this one, can't I add 2 pi to get that one? Okay. How's this one here relate to that one there? 2 pi difference, right? So if I know this one, I can add 2 pi to get that one, right? Well, what if I keep taking this thing on forever? Okay, if I want that one, if I know that one, can I add 2 pi to it to get that one? Which would have been ultimately taking the first one and adding 4 pi to it, right? Okay, so using that idea that they're repetitive with that period of 2 pi, if I want to find the other point here, I'm going to add 2 pi, or another x value, or theta value, another angle measurement that satisfies the equation, I can add 2 pi to it. But then I can add another 2 pi to it, right? And I can add another 2 pi, right? And that formula, I'm going to keep adding 2 pi to it k amount of times. Does that make sense? So what we do is we shorten this and say we're going to take pi over 6 plus 2 pi k and say k is a integer. And if k is 1, I add 2 pi. If k is 2, I add 4 pi. If k is 3, I add 6 pi. If k is 0, I just get pi over 6. If k is negative 1, I get the solutions that are to the left of the y-axis. Okay? Down here, I would add what? Instead of 2 pi k, I'd add 360k. Again, k is going to be, k will always be an integer. Okay? And then here it would be 5 pi over 6 plus 2 pi k. K is still an integer. And down here we would say theta is 150 plus 360k. K again is an integer. Okay? But that procedure, which I think seems kind of cumbersome sometimes, that whole procedure right there are the last two steps of every single trigonometric equation we come across. Okay? Everything else before that, which we'll get into tomorrow and Monday, everything that we would do that leads up to that is replacing with substitutions of equivalent identities, and then maybe using U substitution, or relying on other algebraic skills that we've built over the last 3 years. Okay, I like this section, and I like working with trigonometric equations because it's kind of a culmination so far of everything that you've done in all of your math classes up until this point. Okay, targets everything from Algebra 1, Algebra 2, Trig, college algebra, geometry. It's all encapsulated inside these singular questions. Okay, perfect timing. Have a great day. No new homework. Okay. I probably forgot to copy it to you guys. I'll open it right now. Thank you, too.